Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, good morning, everyone. So first thing first, your quiz this week is based on last week's material, right? So option on futures contract, right? And your quiz next week will be based on today's lecture, Greek letters, all right? Okay, so today we're going to talk about Greek letters. So basically having an understanding of Greek letters provides a way, help us to manage the risk associated with your option positions. So the plan for today is first I'll go through Greek letters, then we'll be looking at some past exam questions, okay, towards to the end of the lecture. I feel like we've done most of the content for this course already, so it's a good time that we start to kind of do some revision, start from this week. Okay, so the main Greek letter we're going to focus on today is delta. And we kind of touched on this delta hedging strategy when we introduced binomial option pricing back in week 5. So the whole point of delta hedging is to maintain a delta neutral position, right? So when I say delta neutral position, I really meant the overall delta in your portfolio sum up to be 0. We don't have any delta exposure. That's what I meant by delta neutral. All right? So to maintain a delta neutral position, you need to constantly rebalancing your position in the underlying asset. And today I'm going to talk about why we need to constantly rebalance our position in the underlying stock. Okay? So first, let's have a look at this hypothetical situation here. So this hypothetical situation says the bank that has sold a call option to a client in this over-the-counter market. Okay? So just to emphasize, this is over-the-counter market. This isn't your typical exchange. And this bank is facing the problem of managing its risk. So it begs the question, what kind of risk the bank is facing? Bank sold a call option to a client, and the bank is worrying about its risk, right? So what kind of risk this bank is facing? Does the bank worry about the price going up, share price go up, or the bank worry about the share price going down? Which direction sounds like a risk? So this is week 9, you should know this already. What do you reckon? The risk that investor will exercise the call option, right? Because the bank has written a call option, which means bank is in a short position of a call option, and whoever holds that call option exercise the option, then the bank lose money, right? Because the call option holder's gain is actually bank's loss. So the bank is more worried about the share price going up, the bank is going to lose money, all right? So let's make that clear. Okay, so let's think about some of the options the bank can manage this risk. So the simplest strategy is simply buying the same option, right? Remember, we short a call option. In order to neutralize our delta exposure, we can simply buy a call option, buy the same call option. Then we kind of get rid of this exposure to the short call. But the problem here says this call option is sold in the over-the-counter market. Over-the-counter market means this isn't an exchange, right? If it is an exchange, the chances are this call option is highly tailored to the client's needs. So this is a not standardized call option that you can find on exchange. In other words, the bank cannot buy the identical call option from the over-the-counter market. So the first option is not available to us. Okay, as I mentioned, this is a highly tailored call option. This isn't your typical standardized call option that you could find on exchange. So the first option is out. What about the second option? So the second option is so-called stop-loss strategy. So let's have a look at this graph here. Stop-loss strategy is kind of simple and naive. Basically, what's going on here is that, so using our example, the bank sold a call option. Just imagine the call option has a strike price of K, right? So the call option allows the option holder to buy 1 unit of stock at a strike price K. Well, the stop-loss strategy is simply buying 1 unit of stock as soon as the stock price gets above K, and selling the stock as soon as the stock price falling below K, right? So let me reiterate. So the whole idea here is the bank would hold a covered position if the share price moving above the strike price K. When I say covered position, I mean selling a call at the same time holding the underlying shares, all right? That's covered position. And then having a naked position as soon as the share price falling below K, all right? So naked position simply means you short a call without holding any underlying share, all right? So that can be a naked position. All right, so the procedure designed by this way is to make sure that in time t, in the maturity date of this call option, the bank would own the stock if the stock price gets above K, if the call option becomes in the money, and doesn't own the stock if the call option finished out of money. So that's the whole ideology behind this stop-loss strategy. It sounds simple enough, and it seems like you can do it, but there are problems to this stop-lossing strategy as well. What kind of problems? What kind of problem you're facing if you're the bank and you try to implement this stop-loss strategy? From foundation finance, you must learn something like efficient market hypothesis, right? EMH. So what does EMH tells us? Efficient market hypothesis. Essentially, EMH has 3 forms, right? So weak form means the market is weakly efficient. Then we have semi-strong form. Then at the top, we have strong efficiency, strong form. So maybe we're not worried about semi-strong or strong. Maybe let's just focus on the weak form of market efficiency. What does it tells us? What does weak EMH tells us from your foundations of finance course? Weak form suggests that any historical info will provide no use for you to predict the future share price. In other words, the stock price cannot be predicted in a weak form. Even in a weak form, we cannot predict the stock price. So the problem faced by the bank is that the bank don't know the exact timing of the share price, right? So the bank cannot precisely capture the timing that the share price just slightly get above K or slightly get below K, right? The chances are the bank would trade on this signal with a lag. What do I mean by a lag? That means when the share price gets above K, the bank, instead of buying the share price at the price K, the bank would be buying the stock price with a K plus an epsilon, plus an extra amount, okay? And instead of banking selling at the price of K when the share price decline, the bank would sell at a price that's slightly below K, which is K minus an epsilon. In other words, this stop-loss strategy cannot be implemented with precision because of the efficient market hypothesis. So that's the first problem. And the second problem is that this is just the oversimplified graph of how stock price move day in and day out, right? So in the reality, the path of the stock price would cross this K, would cross this strike price level many times during the day, right? It would cross this line thousands, millions times during a day. Then this strategy can turn out to be quite expensive, right? Because each time when the share price gets above K, you're going to pay the transaction cost, you're going to buy the underlying share expensive, and then each time the share price gets below K, you got to sell the underlying stock, you pay the transaction cost, and also you incur the price impact. What do I mean by price impact? The very fact you're selling the stock, you're knocking down the stock price. So that's additional price impact that people have to take into account. So the stop-loss strategy isn't really nice. It's time-consuming, you have to monitor the stock price day in, day out, it's expensive, and it comes with imprecision. So the stop-loss strategy is not really an option, right? So we rule out option number 1, we rule out option number 2. Then let's get to the stuff that we're really familiar with, which is delta hedging. Okay, so we kind of did this delta hedging strategy back in week 5. I felt like this is a good time for us to have a quick recap on this example again. So imagine the current stock price is $10, all right? And at the end of one period, the stock price would either go up to $13.50 or you go down to $7.40, okay? So the risk-free rate is 5% continuously compounded. And as the bank, we just sold 1 unit of call option with a strike price of $8, okay? And it matures in 1 year's time. So how many shares we have to purchase in order to neutralize our position? When I say neutralize, I really meant that by buying how many shares that we are not sensitive to the changes in the underlying share price. Okay, remember, so this is the graph, right? So we start with the stock price $10 today in present. Then the stock price can either go up to $13.50 or the share price will go down to $7.40. If it go up to $13.50, remember our strike price is $8, right? So you go up to $13.50, that means our call option is in the money, and the call option will provide option holder $5.50. So option holder's gain is our loss, right? We're going to lose $5.50. So that's why when the share price go up to $13.50, we lost that much. So there's a negative sign in front of the C. All right? But then that's okay. We're going to buy the underlying stock, right? So the whole idea is that if the share price goes up, although we're losing money on the call that we shorted, but we're also making money on the long position in the underlying share, right? So we're going to long delta amount of shares. So delta is the amount of share that we're going to buy, and the delta is the weighting. So weighting times the share price. Then we pay out $5.50 to the call option holder. So that's the payoff to us as the call option writer. Then if the share price go down to $7.40, then the call option finish out of money, right? So the call option finish with a value of 0, and we're still getting delta times the share price that in a down state, right? So we have the share price in the up state, we have this share price in a down state. So that just presents the payoff to us as a call option writer. So we want to carefully choose the delta so that the payoff that produced from this portfolio in the up state is equal to the payoff from this portfolio in a down state. So that's basically what I said. We want to carefully choose the delta amount so that the up state payoff is equal to the down state. And we know what the up state is. As I mentioned earlier, up state is simply delta, the weighting in the underlying share, times the share price in the up state, $13.50. Then we pay out $5.55 to the call option holder. That would equal to the payoff in a down state, which is simply the share price times delta. And that's easy because we have one equation and one unknown. We can simply solve the delta, and the delta to be 0.9. Okay? So delta is 0.9 means that by buying 0.9 unit of shares, our portfolio is guaranteed to make a fixed payoff in time t. We can actually check that. So let's check. If we buy 0.9 amount of shares, so that times the share price in the up state, then we pay out $5.50 to the call option holder. Our payoff end up with $6.67. So that's in the up state, right? Now, if the share price goes down to $7.40, so $7.40 times 0.9, again, we end up with a payoff of $6.67, right? In other words, by buying delta amount of shares, our portfolio doesn't have any risk. Our portfolio just acts like a zero coupon bond that making a fixed payoff. So in other words, to summarize this, by buying delta amount of shares, we neutralized our delta exposure. It neutralized delta exposure in the sense that we are not sensitive to the change in the underlying share price, okay? So despite the fact that share price would change in 1 year's time, we would always get this certain payoff, $6.650. So that's the whole ideology behind the delta hedging, right? So delta hedging is about removing your exposure to the delta. I'll come back to that point in a sec. But let's have a closer look at how we compute delta. So this is our equation, right? So we wish to have the upstate payoff equal to the downstate payoff. Now, if we rearrange this equation, having the delta written on the left-hand side, and everything goes to the right-hand side, we end up with this equation here. So just matter of rearrangement with this equation, we're going to end up a formula for delta in a discrete time, right? In essence, this is a discrete version of how stock price move. Now, in a discrete time, we see this is kind of like a ratio, right? This is the ratio. So in the numerator, it's the changes in the call option price. It's the difference between the call option in the upstate minus the call option in the downstate. In the numerator, it's the changes in the share price, right? So the share price in the upstate minus the share price in the downstate, all right? So to interpret that, the delta is simply the rate of change in the call option price with respect to the change in the underlying share price. Okay, so this would give us the delta. So that's just with the discrete time. What about in the continuous time? The delta is simply the changes in the call option price with respect to the changes in the share price. And we know how to get that. In order to get that, simply we take the first derivative of call option price with respect to the share price, right? Then we can get the delta formula. Okay, so we know what the call option is from the Black-Scholes option pricing model, right? So this is nothing new. This is just taken out of the Black-Scholes option pricing formula sheet. So essentially, the call option price is equal to the share price times ND1, right? Minus the present value of the strike, then times ND2. That's the formula we're all familiar with, right? And back to the previous slides, as we mentioned, we try to get a measure that measures the rate of change in the option price with respect to the changes in the share price. Well, the way to do that is simply take the first derivative of C with respect to S. Now, if you do that by using the differentiation product rule, we can get that would equal to ND1, right, plus the S times N prime D1 minus the present value of the strike, then times N prime D2. Okay? Then, with further derivation, we can show this whole component here is in fact equal to 0. Okay? Just with a bit more step, you can demonstrate, we can get to the conclusion that this whole component would equal to 0. Okay? Proving this is beyond the scope of this course. But just trust me, if you do that properly, this whole component will comes down to 0. And if that's 0, then differentiate, say, with respect to S, will end up with ND1. Okay? So that's really handy. The delta on a call option is simply ND1. And the way we get that is by differentiate C with respect to S. It's handy in the sense that you don't have to remember additional formula for your delta, because you know what the D1 formula is. The D1 formula is just the one that provided by the Black-Scholes option pricing model. Then ND1 is just the figure that we look up in a statistical table. So that's how we get the delta formula. Okay? All right, so there are other Greek letters as well. Okay? So for example, the delta is measured the rate of change in the call option price with respect to the underlying share price. So that's us taking the first derivative of C with respect to S. What if we take the second derivative of C with respect to S? Then if you take the second derivative, that just gives a measure of delta sensitivity to the changes in the underlying share price. All right? And we know the first derivative is simply ND1, then the second derivative is simply differentiate ND1 with respect to the share price. So that measures the second derivative of C with respect to S. That's our gamma. Gamma measures the delta sensitivity to the changes in the underlying share price. Well, then there we have VIGA. So VIGA basically measures the changes in the call option price with respect to the volatility. Okay? Now, to get that, we simply differentiate C with respect to sigma. Sigma is our volatility, right? If you do that properly, you will get the share price times M prime D1 times square root of time T. Okay? So just to remember, VIGA measures the options price sensitivity to the changes in the underlying share price volatility. So VIGA is all about volatility. Now, theta measures the option price sensitivity with respect to time to maturity, or time decay, if you like. To get that, we simply differentiate C with respect to T, right? Then we get this expression here, the risk-free rate times the present value of the strike times ND2 plus the present value of the strike times N prime D2 times sigma divided by 2 times square root of time T. It's a cumbersome formula, but essentially theta just measures the option price sensitivity to time to maturity, to the time, holding everything else constant. While the rho is measure the option price sensitivity to the changes in the risk-free rate and holding everything else constant. And you know the drill. To do that, is simply differentiate C with respect to the risk-free R. Then we will get this equation here, which is T times the present value of the strike, then times ND2. Okay? So those additional Greek letters will be utilized by the fund manager to manage the risk. And I'll come back to the gamma. So why we need gamma in addition to delta? Because sometimes delta is not good enough for us to manage the risk. I'll come back to that point. But our main focus today is mainly on delta, right? We derived the delta formula, and we learned the delta hedging is when you short a call, you need to buy the underlying share. But how do we interpret delta intuitively? Or maybe give the delta an economic interpretation. So let's have this look this example here. So assume the delta on an individual call option that written on a stock is 0.5. So how do we interpret this 0.5? How do we interpret 0.5? So as I mentioned earlier, delta really measures the changes in the call option price with respect to the share price, right? So how can we give this 0.5 an economical interpretation? Right? If you think about this more carefully, delta just measures the option price sensitivity to the share price, right? Or the rate of change in the option price with respect to the share price. Well, 0.5, the way you interpret that is that if the price of the underlying asset changed by a small amount, then the option price will change half of that amount. Okay? So let me say this again. For example, if the underlying asset price goes up by 10 cents, then the option price will go up by 5 cents. So 50% of that amount. But delta only work well for a small change. For a small change in the underlying asset price. Why? So here is the graph. I'll tell you why it only works for a small change. So here is the graph. So basically, the graph is plotting the call option price against the underlying stock price. Okay? So if we plot that, it's not surprising there is a positive relationship between the call option price and underlying share price. Right? It's not surprising because we know if you're the holder of a call option, if the share price increase, then the value of your call option would increase accordingly, right? So there is a positive relationship, that's for sure. But have a closer inspection at this graph, you notice this is a convex graph, right? It's a nonlinear relationship. Why is nonlinear? Okay? This is because when the share price become higher and higher, so for example, when the share price go up higher and higher, then the option price is increasing at exponential rate. This makes sense because once the call option is in the money, once the share price is high enough, get above the strike, then the call option price would become a lot more excited, right? So the call option price would increasing at a higher rate. And if we focus down here, the lower half of the graph, you notice that the option price is increasing at a lower rate. That is because when the call option is out of money, when the call option is out of money, when the share price is below the strike, then the option price is less excited to the changes in the underlying share price, right? So that's why we have this convex graph here. Now the delta is the slope, is the tangent on this point, okay? So basically the delta is a linear approximation of this nonlinear relationship, right? For example, if the delta is 0.5, that simply means we're taking a tangent on this point and the slope is equal to 0.5. So that's why the delta only works for a small change in the underlying share price. Why? Because you see, if the share price changed by a larger magnitude, for example, from A to something like C here, right? So if changing from A to C, then this gap between the nonlinear curve and our straight line, this gap here is not captured by the delta. So that's the imprecision convex delta. Now, if the share price changed by a small amount in this region here, then our delta work reasonably well. Okay, so that's why the delta only works for a small change in the underlying share price. Does it make sense? And also, you see, because the share price change a lot, change throughout the day. So if the share price go up here, now if we take another tangent here, then we're getting a different delta, right? So the delta is higher. For example, we take another tangent on this point, the delta could be 0.8. As I mentioned earlier, because when the option is in the money, the option price becomes a lot more excited, right? So the delta up here is 0.8. Delta in this middle point let's say equals to 0.5. Now imagine if the share price drop a lot, drop to here, we take another tangent, delta could be 0.2. So delta, this concept is not a constant concept. Delta is changing all the time. Delta is changing based on the share price. So that means even if we establish the delta neutral position, for a short period of time, it only works for that short period of time. Over time, when the share price changes, you have to rebalance your position in the underlying share price to make sure your portfolio is delta neutral again, okay? So the delta hedging strategy requires constant rebalancing for the reason I just mentioned, because delta is changing all the time, because the share price is changing all the time. Does it make sense? Does this make sense? The delta is not constant. So any question on this graph or any question on delta? Okay, so as I mentioned before, the way we measure the delta is simply take the first derivative of the call option price with respect to the share price. Then that just boils down to ND1. So ND1 is from our Black-Scholes formula sheet. And as I emphasized earlier, the delta only works for a small change in the underlying share price. Because I mentioned earlier, the reason it only works for a small change is because the delta is simply a linear approximation of this convex payoff diagram. Okay? And if the underlying asset changed by a larger amount, whatever strategy you put in place doesn't work very well. So that's another problem with the delta hedging strategy. Okay. So let's have a look at this numerical example here. So the question says, assume that the stock has a current stock price of $10 and a call option written on that stock is valued at 20 cents. So on one day, the spot price of the stock increased by 2 cents, so increased from $10 to $10.02 cents. Then the call option price increased by 0.8 cents. So increase from 0.2 to 0.208. Then, as I mentioned earlier, the delta in the numerator, the ratio is the change in the call option price. So change from 0.208, change from 0.2 to 0.208. And the changes in the underlying share price is from $10 to $10.02. Then you work out the delta is 0.4, right? And as I mentioned before, the way we interpret this 0.4 is that if the underlying share price changed by a small amount, then the option price will change 40% of that amount. So that's how we interpret the delta. Okay, now, this is the situation where we take a long position in the call option, right? So take a long position in the call option will give us positive delta. As I mentioned earlier, because if you are the holder of the call option, as the share price increases, your call option price also increases. So that's a positive correlation, right? Positive delta exposure. So how can we neutralize this? How can we get rid of this positive delta? Now, we're now exposing to a positive delta, and my goal is to achieve delta neutral. So delta neutral means that we have an overall delta of 0 in our portfolio. So how can we get rid of this positive 0.4? How can we get rid of this positive 0.4? We simply find something with negative delta, right? We simply find something with negative delta, then we combine the positive delta with negative delta, then we achieve delta neutral, right? We know buying 1 unit of stock is always going to give us a positive delta of 1, right? So how can we create negative delta? You simply short, right? So shorting the share gives you negative delta exposure. And how much you're going to short? You're going to short 0.4 shares. So instead of shorting 1 unit of share, you're going to short a fraction of that. You're going to short 0.4 of the share. Then shorting 0.4 shares give you a negative delta of negative 0.4. You combine that with positive 0.4, we achieve delta neutral, right? We remove all the sensitivity to the changes in the underlying share price. Okay, so that's basically what I mentioned earlier. In order to achieve a delta neutral in your position, that means we need to constantly rebalancing our portfolio throughout the time. Because as the share price changes, so does the delta, so does the slope on the graph. And we need to readjust our position in the underlying share to always make sure that the positive delta, negative delta combined together give us 0 delta. So another example here. So the question says, a stock is currently trading at $100 per share, and a call option at the current stock price is trading at $10 per option. And you've sold 2,000 call option contract. The delta on each individual call option, the return on the stock is 0.6. If the share price increased by $1, then the price of your call option would increase 60% of that, which is 60 cents. So if you wanted to close out your position in the option, you would have to pay somebody $10.60 to take your short position in this call. And with $1 increase, each $1 increase in the share price, you're going to lose 60 cents in the call option, right? That makes sense because you're the writer. So how are you going to create a delta neutral portfolio to manage this risk exposure? So as I mentioned, when we take a long position in the call, and if each call has delta of 0.6, we're getting a positive delta exposure, positive 0.6, right? But in this situation here, we short call. Short call, that means we're getting negative delta exposure, right? And how much we shorted? We short 2,000. So that's 2,000 times 0.6. So our total delta exposure is negative 1,200. It's negative because we short call, right? Because long the call would always give you positive delta, then short call give you negative delta. And the total delta comes down to 1,200. So the situation here is we need to find something with positive 1,200 delta to neutralize, to cancel out this negative delta. Well, the best place to find positive delta is the underlying share, right? So buying 1 unit of share always give you positive delta 1. That makes sense because when you plot the share price against the share price, it's always, perfect 100% correlation. So that comes down to positive delta 1. Okay? So in other words, we need to buy 1,200 shares to create positive 1,200 to cancel out this negative 1,200 delta. In that sense, we achieved delta neutral, right? So that's our strategy. Then let's have a look at 2 scenarios. The first scenario is where the share price go up, and we see whether our delta hedging works. So it says, if the share price goes up from $100 to $101, then because we have a delta of 0.6, then the call option price would increase from $10 to $10.60, right? So how much we lost on the call option? Remember, with the writer of the call option, we short 2,000 options, so we lost $1,200 on the 2,000 call option that we shorted, right? So we lost 1,200. But that's okay, because we bought 1,200 shares to create positive 1,200 delta, right? So we actually made $1,200 gain in the underlying stock position. So the positive gain cancel out the loss in the call option, so the net position is unchanged, right? So you are insensitive to the changes in the underlying stock price. So that's the first situation. Now let's have a look the opposite. What if the stock price decrease? So if the stock price decrease from 100 to 99, then our call option will go down 60% of that, will go down 60 cents. So decrease from $10 to $9.40. Then we actually made a gain of 1,200 on the call option, right? Because as the call option writer, you make money when the underlying share price decrease. So we made positive 1,200. And in this situation here, because the underlying share price goes down, and we bought 1,200 shares, so we lost $1,200 on the stock position. So again, the loss and the positive gain cancel out. We are not sensitive to the changes in the underlying share price. So that's how we achieve a delta neutral position. So we are no longer sensitive to the movement in the underlying share price. Does it make sense? So any question on this example here? All right. So to sum up what we have discussed, the delta is simply ND1, as we demonstrated before. And so this ND1 represents a long position in a European call option that written on a non-dividend paying stock. All right? So if you short a European call option, then you are creating a negative delta. So the way we cancel out that is by take a long position in the underlying share, and the amount we're going to buy is simply ND1. Right? So ND1 is our delta. We're going to buy delta amount of shares to cancel out the negative delta that we shorted in this European call, as I demonstrated in the previous example. Now, if we take a long position in the European call option, essentially we're creating a positive delta exposure, and to cancel out the positive delta, we simply short the underlying stock. And how much we're going to short? We're going to short the delta amount, which is we're going to short ND1 amount of shares to cancel out the positive exposure in this European call. And then the delta on the European put option is simply ND1 minus 1, right? So the way to remember this is with the call option, you always do the opposite position. So whenever you're shorting the call, you're longing the share. Whenever you're longing the call, you're shorting the share. You always do the opposite. But with the put option, you always take the same position. So what do I mean by that? Well, think about if you long a put, the delta is going to be positive or negative. If you long a put option, your delta is always positive or always negative. Which one? Put option price has a positive correlation with the share price or negative correlation with the share price. Negative, right? So by longing the put option, you'll always have a negative delta exposure. Just to remember that. Now, in order to get rid of the negative delta exposure, so here, long, you need to get some positive delta, right? So the way we create positive delta is by long the underlying share. So that's why we're doing the same position with the put option. Whenever you long a put, you also want to long the underlying share. Because loaning the put always gives you negative delta, and loaning the underlying stock gives you positive delta. So they cancel out. Now, if you short the put, then shorting the put will give you positive delta, right? The reason why it's positive delta is because as the put option holder, you wish the share price to go up. Why? As the put option writer, you wish the share price to go up. Why? Because if the share price go up, then whoever holds that put option will not exercise against you. So that has a value to you, right? So you wish the share price to go up so that the value on the put option you shorted would also go up. Now, you short a put, that would give you positive delta. The way to cancel out the positive delta is by shorting the underlying share. How much are you going to short? You're going to short ND1 minus 1 amount of shares to cancel out that positive delta, right? So that's why I said with the call option, you always do the opposite. With the put option, you always do the same position. Okay, so let's have a 10 minutes break. Then we're going to look at some numerical example after break.